Hi, this is the Connectedness 8 part of Topology series. But a running title for this lecture could be Locally Constant Functions and Connectedness. Okay, and let us see how to do that. Yeah, so let us start with the. Did I start recording? Yes. So let x and y be topological spaces. Let f be a function, just a function, no continuity assumed to start with. Okay, so we say f is locally constant on x if for every a in x there exists an open set ua containing a, so that f is a constant on ua. Okay, notice that therefore that means for every x in ua we should have fx equal to fa, because it's must have constant. So let us take that itself. You understand that? That is for every x. Is that clear? Yeah. So you may ask whether there exists, why won't study locally constant functions? Okay, within topology I can give examples, but I want to give a very important example which occurs in analysis. Okay, so suppose I have U, an open subset in Rn with the standard topology, and f is from U to R. Okay, let's assume it's a differentiable function, right? I can do from Rm to Rn f from vector valued function of vector variables. Okay, but for simplicity let me stick to that, because then all of you know that if f is differentiable, then derivative of f at x will be a linear map from Rn to R, and it is given by dot product with equal to the gradient of f at x, okay, dot product with h. This is del f by del x1 at x and del f by del xn at x and dot product with h1, h2, hn. These are all known. I'm sure you've learned it. Okay, the reason why I want to talk about is, suppose, okay, for all x the gradient del f x in u, del f x is 0. That is, the derivative is 0. Therefore f from u to r is differentiable with the derivative 0, with the 0 derivative, right? So because most of you are kind of brainwashed into believing any function with a 0 derivative must be a constant. Okay, I just want to show that that's not very correct. Okay, let us assume my set u, let me say this is R2, let me assume my set u is like this. Okay, an open disk here, another open disk here, and these do not intersect. Okay, now let me define the function to be 1 here and minus 1 here. Okay, you understand that? So my u is b minus union b plus. This is b minus, this is b plus to r. Okay, and function f from this to r. Okay, and b minus f equal to minus 1 on b minus and equal to 1 on b plus. Then f is differentiable and derivative of f at x is 0. The gradient is always 0, but f is not a constant. Okay, you understand that? So what you can actually show that is using mean value theorem. if f is from u in Rn to R is differentiable with a zero derivative, then f is locally constant. A more general set will also be proved in my lectures on several variable calculus. Okay, look at the video, corresponding video, where I talk about mean value theorem or mean value inequality and its applications. Here, there I prove it. In fact, I actually prove much more general. F from u in Rn to Rm, differentiable with derivative 0. Then it's a locally constant. So this is one thing where it occurs. Right? Okay. Now, the next observation I want to do, the fact is, any locally constant function is continuous. That is, f is from x to y, this is continuous, right? So how do I prove that? Fix a in x, then I have to prove f is continuous at a. Okay, I don't want to go to the usual mantra, inverse image of any open set is open. I can use that, but I prefer this. Okay, suppose f is continuous at a, right? Now, so I have this x, and this is my a, this is my y, this is my f of a. To prove continuity of f at a, what I have to do? I am going to give, you are going to give me an open set B. Okay, so let V be any open set in Y, such that f of a contains f of a belong to B, right? Now what do I know about f? F is locally constant. Therefore, there exists an open set, open neighborhood UA of A, so that f x x equal to f at a. This is true for all x in UA. Okay, that means there exists, this is my UA, and give me any x. What is its value? FA. Therefore, what I have shown? Therefore, there exists UA containing a open set, so that f of UA is contained in V, because this is all a singleton FA. Yeah. So I have proved any locally constant function is continuous. Okay, right. So this is a very trivial exercise. Let x tau x be any topological space, and let y tau discrete, this be a discrete space. Assume, now I am assuming, okay, this is important, assume f from x tau x to y tau discrete is continuous. Okay, notice that to define locally constant function, I did not assume the function is continuous. That was a corollary. But here I'm going to say if f is a function from a space to discrete space which is continuous, then f is locally constant. Okay, so take this as an exercise. Okay, now let's come to the main result of this lecture, the theorem. Let x tau x be a topological space, then x is connected if and only if any locally constant function f from x tau x to y tau y is a constant. You understand that? So what we are doing is x tau x is a topology space. Let y tau y be any topology space. Assume that you give me a locally constant function from x tau x to y tau y. Then I want to say this function will be constant if only if x is connected. Are you following? Okay. Let us prove that. Okay. So assume x is connected. Okay. And let y tau y be a space, topology space, and f from x tau x to y tau y is locally constant, be locally constant. Right? Then what do you have to prove? We have to prove f is a constant. Alright? Okay. So how do I prove that? Yeah? Suppose not. Right? Okay. That means f is not a constant. Therefore there exists y1, y2 in y, y1 not equal to y2, and there exists x1, x2 in x, so that fx1 is y1, fx2 equal to y2. But I should say fx1 is not equal to fx2. That's good enough. It's not a constant. That means there exists 2 points, x1 not equal to x2, so that fx1 is not equal to fx2. Alright? Do you follow that? If it's not a constant, then at least it takes 2 distinct values. That's what I'm saying. Okay? Do all of you understand that? Very good. Now what is that I want to prove? I want to prove it's a constant. Okay, in fact I don't even need this. Okay, forget this. So you can see I am thinking. Okay, I thought of a better way, because this is not, as I said, this is not a very well-known result, but it's a very beautiful result. The reason is the proof which I'm going to give is a typical way in which the connectedness hypothesis is exploited. Okay, suppose you are given me x is connected, then I want to prove something, right? How do I do that? The thing is, so let's fix an a in x. Okay, then I want to prove f is a constant, therefore enough to show for all x in x, fx equal to fa, right? So the result, it's enough to prove prove the results. I need only to show for all x, fx equal to fa. Do you understand? This tells us how to use connectedness. So let's look at a subset E, which is set of all x in capital X, so that fx equal to fa. Right? Is the set empty? No, because A belongs to this. Therefore E is not empty. So next what I show is E is open, and I will also show E is closed in X. Therefore E is a set which is not empty but both open and closed. But X is connected. Therefore what do I know? E must be all of X. If E is all of X, what does it mean? For all X, fx must be equal to fa. That means f is a constant. Do you see that? This is the typical way you try to exploit the hypothesis of connectedness. Whatever is the result, final result you want, using based on that result, you try to think of a set, a subset. Yes, and make sure that set is non-empty and try to show it's both open and closed, and therefore that set will be all of X. Therefore your result must follow. Okay, this is vague, but I'm just giving an abstract strategy, but you are going to see how it works here. Okay, right, now let's prove this. Suppose X is in E, right? I want to say E is open. First thing is E is open, so let X belong to E. Then what, remember when I talked about open sets etc., I gave a recipe. When I want to say a subset U of X is open, what is the trick? for all x in U, I should find a ux, an open neighborhood of x, that is okay, so that x belong to ux and ux is contained in U. Therefore U will be union of ux as x varies over U, therefore U will be open. Do you remember? This is the trick. Almost 99.99% of the time when you want to say abstractly a subset is open, this is the only way. So I want to prove E is open, therefore let x be in this. So what do I have to do? I have to find a open neighborhood so that x belong to ux and ux is contained in E. If ux is contained in E, since x is in E, what do I know? Fx is fa, right? And when a ux is contained in this, that means what? If x dash is ux, then fx dash also should be equal to fa. This is all I have to prove. Do you understand? But that's very easy. Where will I find such a ux? Remember, f is locally constant. Therefore, since f is locally constant, there exists ux, an open neighborhood of x, so that for all x dash in ux, we have fx dash equal to fx, right? Just because of local constantness, right? Therefore, for all x dash, but what is fx? That is fa. Therefore, what happens? For all x dash in ux, I have fx dash is fa. That means for every x dash in ux, x dash is an element of E. That means ux is contained in E, right? That means E is open. Yeah, pause, review, proceed. Now I want to show you E is closed. Again, if you have followed my lectures, the best way to prove as a set is closed is look for adherent points. So let x in x be an adherent point. Point of view. Okay, we need to prove x belong to E, right? Okay, now let's go. Since x is an adherent point, okay, right? Now f is locally constant. Therefore, there exists open neighborhood of x, so that for all x dash in ux, I have fx dash equal to fx, right? Okay, but just because a local constant, I got ux. But what do I know about x? X is an adherent point of P. Since x is an adherent point of P, okay, E intersection ux is not empty, right? Therefore, there is a P which is in E as well as in ux, right? Now, since P belong to ux, I know f of P must be equal to f of x. But P belong to E, therefore I know f of P equal to f of A. Therefore, what do I conclude? Okay, both these things imply f of x must be equal to f of A, but that in turn implies x is an element of E. Therefore, every adherent point E belongs to E. Therefore, E is closed, right? So what have we seen? So E is not empty, E is open and closed. Since x is connected, we conclude E is all of x. That means for every x in E, f of x must be f of a. That means for every x in x, f of x is f a. That means f is a constant. Okay, is the proof clear? So go through this particular argument. This is the typical way you will use connectedness. That is one of the reasons why I wanted to give this lecture. Okay, in the simplest case, so that where you will actually learn, okay, how to work with connectedness hypothesis. We will see one or two more examples later also within connectedness itself. Okay, at least two examples I will show again. Okay, now converse. What is the converse? Converse is assume that, let me write it, any locally constant function on x of x is a constant. Then I have to prove x is connected. Is it okay? Right. So what is our criterion for connectedness? So let f from x to R be continuous, so that f of x is continuous plus or minus 1. Okay, remember this is a continuous function into the discrete space plus or minus 1, therefore f is locally constant. Okay, so be focused. I want to prove x is connected. That means you are going to give me a function f from x to R which takes values only in the discrete space set plus or minus 1, right? Therefore f is a continuous function from x to the discrete space plus or minus 1, and we had already seen, okay, any continuous function into a discrete space is a locally constant. Therefore in particular f is a locally constant, right? You follow that? But what is the property of the space? Any locally constant function is a constant, therefore f is a, okay, hence by hypothesis f is a constant. You follow that? That's it. Do you understand the proof? Go through that. It's a very beautiful, very simple minded lecture, but it teaches you how to use connectedness. Okay, so this is an optional thing, so if you want you can even skip it. Okay, right. So let me stop the lecture. So this lecture may be optional, but the proof I like it because it teaches us in a very simple way how to use or invoke or exploit the given fact the space or set is connected. Okay, you will see in your complex analysis courses, and you will again see in our course also one or two more occasions I will use this result. Okay, so take care, stay safe, we will meet again.